So that leads us into the bulk majority of this lecture, the cerebrum. It's the bulk majority of the brain, right? So it would make sense that this is going to be the bulk majority that we are going to be talking about. All of, again, it's like 80%, I think, all of our abilities to interact with the world, interpret, understand senses, initiate motor commands, good and evil, all of that's here within the cerebrum. Frontal lobe, parietal lobe, temporal lobe, occipital lobe, the insula. All of these different regions of the cerebrum allow us to interpret all of these special and general types of sensations. So we can interact with this world properly. We have a number of folds called gyri, plural. Gyrus would be singular. And these folds are fantastic. These are where all of our nerve cell bodies are going to be found up there. Okay? It's gray matter up there. White matter is internally. White matter is going to be more myelinated nerve fibers. That's not to say there's no cell bodies scattered throughout, because there are. And they would be gray in nature. But if I don't get all those gyri formed at the right time, because I don't really know that I'm pregnant and I'm not going to eat much, and I don't eat any fats or consume a lot of fats, and I'm not taking folate, these gyri don't form either. And that's called lissencephaly. It means smooth brain. So all of these folds are vastly important when it comes to your development. Okay? And you can see this a lot in maybe mothers who don't know they're pregnant. You can also see it with certain dietary patterns as well. So it is something that you don't want to be very restrictive in your diet if you don't have to be. So we got gyri, sulcus, sulci would be plural. These are the shallow little grooves that separate all those gyri that you see right there. Okay. Sulci are shallow. We have fissures, right? Fissures are really deep. We have deep fissures, as you can kind of see right there, longitudinal fissures. Okay. We also have deeper sulci as well. The central sulcus, the lateral sulcus. Those are the two kind of major ones, and you can really see them. They're kind of, central sulcus is pretty important to kind of understand because it's the line of demarcation between two very important structures that we're going to talk about here in a second. There within the cerebral cortex, we have that central sulcus, and it is what helps to separate the frontal from the parietal lobes. The big old fold right in front of and right after central sulcus gives rise to what we call our precentral gyrus and our postcentral gyrus. This houses an important region of neurons called the primary motor cortex and the somatosensory cortex, or the primary somatosensory cortex. As you might figure out, primary motor cortex initiates all of our motor commands for skeletal muscles for the most part. Postcentral gyrus has that primary sensory cortex, or the primary somatosensory cortex, and this is where all our general types of sensations are going to. Primary, they're extending down from. Somatosensory, we're going up to. Okay? This is just general sensation. So touch. That's what we're talking about here. This is not special. Okay? All the special senses are done in specific regions and multiple other various lobes. Okay? So all of that sensory input that we're going to start talking about a little later next week goes up to here to be interpreted. After we figure out what it is, oh my gosh, it's really hot, I should pull my hand away. Then we send information to the primary motor cortex that goes to the arm muscles, and we contract the bicep and move the hand away from the open flame. And here's what these two regions look like. Okay. There's your little sensory and motor homunculi. But you can see it's really not even at all. Is that okay?
Yeah.
Why?
Well, because this medicine, well, I'd imagine that not all, some areas of the brain take more processing power and or space than others. And so that's why the somatosensory is bigger, is because it deals with, or it can deal with like some senses, whereas the motor cortex is just really movement and may not require as much space.
You're ballparkish. You're kind of right. Kind of wrong. You're kind of right though. I like what you're thinking. But like, look at, let's compare something here. Look at the face. Okay. Look at the face. I mean, the face is a pretty important thing, right? Well, they're all important. We have the face, and the face is pretty, there's a pretty good chunk of real estate carved out there in the brain for motor. There's, okay, I mean, it's big in the somatosensory cortex, but it's not as. But when you're looking at these two things and you look at the amount of real estate that's carved out in the brain for, and we'll look at the motor cortex, look at the left there. My trunk, I don't have a whole hell of a lot of real estate carved out there. I mean, my trunk seems like it's pretty important. My face seems pretty important. Wouldn't it stand to reason that pretty much everything would be pretty even? But no, right? Movements are not the same. Movement of my hand is not the same as my back. I can pick up a pen or a pencil pretty damn easily. I can't really do that in my back. If I could, I'd be in the circus and I wouldn't be here. So in the regions of the brain where I need much more precise control, I have a lot more real estate. With precise control, you should immediately start to think of those things that you looked at when you're talking about muscle, motor units. We have small motor units, we have large motor units. Small motor units are very precise control. I have one motor axon going and supplying anywhere between 2 to 5 muscle fibers. That's really precise. But I'm only engaging 5 muscle fibers, so I'm not really producing a whole heck of a lot of movement, or I'm not generating a whole heck of a lot of force, I guess I should say. Whereas in my calf muscles, I have a very large motor units. I have an axon that supplies roughly around 1,000 muscle fibers. So I can produce a whole lot of force. There's 1,000 muscle fibers engaging, but it's not very precise. So in regions of the brain there in the motor cortex, the areas like the face, the mouth, the hand, these have a ton of real estate. We communicate so much. Look, there's so many little things going on with my face and with my hands. And I can't do that with my arm. I can just flex and relax. My back, it's just, that's all I'm doing. Okay, that's not really precise. Same thing with the somatosensory cortex. There, I have a ton of real estate, as you can kind of see, carved out for the hand. It looks weird. See, so is the face, even more so really for the lips, the tongue. There's so much sensory. And this is going to go to a concept that you may have touched on in the nervous system, but receptive fields. Receptive field, the bigger the field, the much less precise you can get with something. The smaller the receptive field, the much more precise you can understand and know what's creeping and crawling on you. And regions of the body there, like the hands, the face, okay, I can take two pins and I can get them a few millimeters apart from one another before you're like, eyes closed. As I'm doing this, I'm kind of poking your hand. I'd say face, but it's not nice. But poking your face there, and you can get really close. And you'd be like, okay, there's only one pin touching me now. Your eyes are closed, and there's two pins on you. And that goes to a very, 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 very small receptive field. And places like the hand and the face have a lot of real estate, a lot of nerves, a lot of space, only a small little space that it's governing for every little nerve. So I have more real estate there. In areas like the back, you can get like damn near 2 or 3 inches apart a lot of times and be like, okay, there's only one thing touching me, but there's two pins clearly touching the skin because these receptive fields are much larger. So it's not as precise. So when we start talking about these concepts, when we get into receptive fields with touch, when we get into the precise motor control, when we talk about motor control options, it's going to come back to this little thing right here in this pre and post central gyrus respectively. My other lobes, they're going to do some stuff. Temporal lobe, auditory. We'll talk about interpreting auditory sensations when we talk about special senses. Occipital does a lot of stuff. Vision cortex is generally found here. It will be involved with helping to get images to focus properly. So it'll help coordinate a lot of eye movements, which again is going to be kind of governed by cranial nerves, especially. The insula is kind of this kind of catch-all area. It is this, as you can kind of see there, taste, smell, auditory a little bit as well, pain, all of that gets interpreted here. Memory as well. So we'll talk about the insula. It's the amygdala, it's the hippocampus. But the insula is important because it helps coordinate the encoding or the hard wiring of a memory. And it does that through a lot of cool, fantastic things. So, and we'll talk about that a little bit because that's really the coolest part of this. You can visualize all this. Okay. You can visualize all this. You can use an EEG, an electroencephalogram. Okay. That's what it's called. Let's see here. There are 4 major patterns that you can visualize, and you can see them listed right there. Some of these are much more common in adults. Some of them are a little bit more common in children. These are fascinating things. If with bedwetting and whatnot with children, you see certain types of waves that you're not supposed to see, when they are sleeping. It's an overactive brain. We don't really understand a whole hell of a lot of stuff when it comes to the mechanisms as to why this thing affects this thing. We know it does, but we don't understand the full mechanism. And memory is one of those things that we're starting to get a lot better grasp on. And a lot of learning techniques are geared to that new science that's been coming out over the last 10, 20 years, 30 years that I mentioned earlier. But we have alpha waves, beta waves, theta, these crazy delta waves. It's these two that are pretty much seen in sleep. Okay, kind of all over the place. I don't necessarily care a lot about what area of the brain, because that's really way above and beyond. But these are the waves that you primarily see when you are sleeping. So that's what you want to see. If you don't see those waves when you're sleeping, that's when you're going to have some potential issues. Could be some memory issues, because sleep is vitally important for the making of a memory, we are learning. Alpha and beta waves, these are going to be more present when you are awake. Some are more prevalent when the eyes are open. Some are more prevalent when the eyes are closed. There is so much semantics when it comes to these 4 different waves. And even 13 is about the magic number. Whatever happens at 13, stuff starts to happen in a brain. As soon as we figure out if we're having a boy or girl because of, the Y chromosome, then we have hormones get released, and that starts hardwiring the brain to be a certain way. It's called masculinization of the brain. So that's kind of this first hardwiring. Then the child's brain, they have a hard time reasoning and understanding. We all know that if you've been around children at all. But that prefrontal cortex is vitally important for that. And that's one of our regions that, decides good and evil for us. Okay. It's bad to take my pencil and go jab Sam in the face during class because he asked a stupid question. Okay. That's bad. I know that's bad. That's my prefrontal cortex telling me that. So if that's screwed up, that may be normal. And I wouldn't do it the same. I like his questions. But these wave patterns start to change and start to normalize a little bit after the age of 13. Why? I don't know. I've been trying to look that up over the last few weeks to try to figure it out. I can't find it. It's just, we know at age 13, we see these wave patterns that are more geared to adults actually start to kind of manifest and take shape at around that 13 years of age. Is that because connections in there are starting to form a little bit better? Maybe. I don't know. But our understanding of this whole thing that is the brain, we just learn more and more and more every 5-10 years. And it's fascinating. Like even in the book, it'll say like, this is what happens. But dang if I know. And there are several areas in the body that are like that. Kidneys. We know a lot of stuff with there. But some of the mechanisms were just like, I see this and this, but I just can't see it right there. And the brain is one of those things. Okay. It's very dynamic. It can shift very easily. If you have brain damage when you're young, the other parts of the other side of the brain can manifest those centers and start handling speech, which is usually only found on the left side. Have that same damage in an older person, maybe SOL. So the brain is this fascinating creature, and our EEG is the way that we can visualize how electricity is moving in different parts of the brain. Again, sleep is vitally important. Okay. You're all adults here. How many of you get 7 to 8 hours? Andy, how much? Nah. 7, 8? Look at
9.
you. Sam, what do you do?
Get 9.
9?
I think I got 8 last night.
That's awesome. That's why you guys are in this class, because you guys are smart. 7 to 8 hours. If you do not get that, or if you go to bed, how many of you go to bed at like midnight, 1 in the morning? Eric, guys, don't do that. There are different chemicals that get released in your brain when you stay up late. We're finding that hardwires you to go find certain types of foods that are bad for you. So don't do it. Or if you do stay up late, have great control. But who has great self-control at 2 in the morning? I know I don't. Okay? Or I do. I'm a responsible adult.
That's why you go for the bag of shredded cheese.
Right? You're hardwired to find really carby, starchy stuff. There's a few different hormones and secretions that happen in the brain that hardwire you to find carby foods. It's pretty interesting and fascinating, that concept. But as you can see, when you're an infant, all you do is sleep, poop, eat, sleep, poop, eat, sleep. That's it. See, teenagers, good gosh, 8.5 to 9.5 hours. That's a lot. And it's crazy if these children, teens, still a child, are staying up late. I mean, this really affects, as you can see there, a lot. Depression, immune function. But the biggest thing we're finding out is that 7 to 8 hours is the minimum that you should be getting as an adult to help with memory. My oldest has really difficult times. He's a toss and turner. He's ever since the very beginning. He's never been the best sleeper. And that's, again, he's 13. So he doesn't remember, where he put his phone, which, is right next to the computer. So, he's a space cadet half the time anyway. But it does. You can see when he doesn't get that sleep, you can see he is grumpy. That's not depressed, but I mean, his mood changes. When he goes through a period where he's sleeping really well, he does a great job at remembering things, school related. So we are finding out that sleep is key to that. And we'll see that concept here in a second and what it actually does. There are a number of neurotransmitters involved with it. Histamine, I mentioned that one because histamine we'll talk about with the immune response later in the semester. It's involved with helping you to wake up. So as soon as you open your eyes, it's that histamine that's going to start being secreted to help stimulate the brain to wake up. Reticular activating system. There are a number of other things as well that go into that. But histamine is the neurotransmitter that's doing it. GABA and adenosine, but GABA, since we mentioned that earlier, it's going to be involved with helping to promote sleep. Serotonin, okay, melatonin, right, with your circadian rhythm, helps you to be awake when it's light out and asleep when it's dark out. And we'll talk about that a little bit here in this. We'll talk about it a heck of a lot more with the endocrine system. But serotonin, once you are asleep, serotonin helps to get you in and out of REM and non-REM sleep. And getting in and out of those two stages of sleep are important when it comes to memory. Cleaning up. If you're awake all day long doing stuff and you don't clean up, the next day you wake up and your house is a shambles. God dang it, I got to do all this work again, but I got to clean up this work first. And that's basically what sleep is allowing the brain to do, to turn itself off and clean house. When it cleans house, cleans up all the free radicals and all the nonsense that's happened over the course of the day, it goes in and it massages basically these nerves that we utilize today as we memorize our notes from last class period. And it helps to massage these nerves, strengthen these nerves up to make it easier for us to recall this nonsense. And if you don't get that sleep, if you don't get into REM and non-REM sleep and bounce in and out of it, that affects performance. And that's stuff that they've started to see as they increase the ability to do these sleep studies and understand what's being secreted and what is happening on a very, very, very small level. So here is non-REM and REM sleep. You can see the vast majority of our time is spent in non-REM. It's divided into 4 substages, and there's like 1, 2, 3, and 4. That's their names. And it's characterized by a lot of slow waves. As you can see, they're delta waves. But depending upon what wave pattern we see, depends on what stage you're in. It's important for a lot of things. Okay, it's important for growth, rest, restorative nature for the brain, energy conservation. So there's a lot of cool things associated with that slower frequency there. A lot of cleanup. REM, rapid eye movement, that's what it means. Okay. Not very much. You don't spend a whole heck of a lot of time in REM. We consider this important to help consolidate these memories. Okay. Consolidate means to make something into a long-term type of memory, to remember it the next day. All right. This is where your dreaming occurs, your memorable dreaming occurs. So, and you will go in and out of this. Okay. You don't get in REM, at, mark 30 minutes after you fall asleep. These cycles last anywhere between 60 and 90 minutes, respectively. So, you may spend about an hour or an hour and a half max in REM sleep, and then cycle back into one of the 4 substages of non-REM. And then you may or may not get back there. It just kind of depends. There's a lot of variation. And that whole understanding of it, not quite there yet with that concept. When it comes to that rapid eye movement, this is generally kind of when you are most erratic. This is when you will generally flail around a little bit more. Your breathing and your heart rate get very irregular, like you're huffing and puffing almost, it seems like. Well, there's a lot more emotions. If you ever remembered a memory and woken up and remembered it, okay, and sometimes they can be really real, and your heart will be racing. Your breathing will be very quickened. But we're finding this is helping to consolidate these things called non-declarative memories. Non-declarative memories, it's just kind of this broad term. Habits, skills you may have learned throughout the day, performance. That's what a non-declarative kind of memory is. Your job. If your job is to take the food and run across the scanner every time, there you go. Okay, it consolidates that, lets you know what to do. When it goes beep, 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 you know to look at the screen and hit enter. When it just goes one beep, you know to just to keep rocking through it. That type of thing. Non-REM, this is when it's going to be much more regular in nature. Neurons decrease in firing. This is where we start to get a lot of repair and restoration to the neurons themselves. It helps us with spatial memory, understanding where we're at in space. I know that I'm not supposed to get next to the fire. I remember that. I know I'm not supposed to get next to that big wheel of machinery there. I'm not supposed to put my hand in the jar of mayonnaise at work, space orientation. Declarative is just stuff, facts, events, history, okay? Factual information, that's declarative. If you declare something, you declare facts. There you go, okay? But this non-REM sleep, which is the vast majority of our time, is really where we start to see these neurological changes happening in the brain. Specifically like in the hippocampus, a little bit of the amygdala, perihippocampal region. That's where we see a lot of it, but that's where we see a lot of our abilities to form memories and to form new nerves, actually create nerves. So it's pretty cool. We didn't think that was the case, 20 years ago.